Other questions? The average was like, so far, the average was like a little over 71, so it was pretty good. I didn't think it was a terribly easy test, so you all did pretty well, so good for that. So let's finish strong. Today, we are going to talk about, and this will be section 6.4. The Gram-Schmidt process. And I'm going to do as an application simply called QR-factorization. Oh, and also, while I'm thinking about it, this is another one of these Mondays when I have one of those committee meetings. So if you're going to see me today, you have to make sure it's before 1 o'clock. So the Gram-Schmidt process. What is this for? What does it do? So if you have a basis, your basis might be a bit of a mess, right? You can apply the Gram-Schmidt process to this and take your basis and turn it into a sweet basis, one that is orthonormal, or actually one that's, the way I'm going to teach it to you, you're going to do orthogonal because that's actually easier. My advice to you is when you see some descriptions of Gram-Schmidt in some books, they tell you how to do it, and at every step they normalize it. Don't do this. It's a horrible idea because, well, if you're doing it by hand, don't do it. It's terrible. Right? What you want to do is get the orthogonal basis first, which is bad enough. And at the end of the day, you've got an orthogonal basis. Now it's easy to make it normal. Just divide out every vector by how long it is, right? So it takes a messy basis and turns it into a orthogonal or even orthonormal basis. You want to go that extra thing. And this is important in like Fourier analysis. It's important in all, I mean, when you do partial differential equations, doing things like eigenfunction expansions, it's all very nice to get these bases that are orthogonal. Because remember, if I have a vector and I want to figure out how to express it in terms of a basis, I have to set up a bunch of equations, right? But if I have a vector and I want to express it in terms of an orthogonal basis, all I have to do is do a bunch of dot products and divide out by some lengths, and bam, it gives you the coefficients. That's why you would ever want one of these things. Let me describe this to you. I'm not going to prove the Gram-Schmidt process because the proof almost goes in the pictures that I'm going to draw here and in the process itself. Right? I can't put it any way around. Now, this is a basis for the chalkboard plane, right? Because these are two vectors that are linearly independent because they're not on the same line. So everything on the chalkboard, and in fact, everything in that plane forever that goes down to Hades, up to heaven, spread out from the chalkboard, I can express in terms of those two vectors, right? But it's not as nice. I would much rather have this basis. I would much rather draw perpendicular line. Yeah, putting that box in this perpendicular. So now if I replace x1, I'll leave x1 alone, and I replace x2 with this white vector, it's still a basis, isn't it? But now it's at right angles, right? So if I have two vectors, you've already done the Gram-Schmidt process because what do? You take the orthogonal projection of x2 on this, and then you subtract that off of x1, right? Or you subtract that from x2, is what I should say. Okay, so what about three-dimensional space? Well, suppose I've got this plane here. And suppose I have two vectors here. Right, that define this plane. Well, I already know that I can kind of realign things and make this so these are rectangles. All right, now what if I have another vector that comes up out of this plane into space? Well, now I'm sad, little Jimmy, because here's my problem, right? The yellow and the white in this plane will orthogonal to each other, right? And these three vectors are linearly independent because these two are, and this one, this red one's not in the plane of the first two. Agreed? Gosh, I'd like to have an orthogonal basis to this as well. Well, what did we do? Just get the vector projection of the red vector into this space, right? And subtract that or take this and so let me see if I can draw this well. If I've done this right, this should be this. I've done it very well. But the vector projection here will be this right here, the shortened version. And now I've got the third one perpendicular, right, parallel to this one. So this is basically the Gram-Schmidt process. It's just step by step. If you've got two vectors, take the projection of this one onto this one, and whatever that vector projection is, take this minus the vector projection, and you get that one. Now, in a plane, if these two aren't perpendicular in the first place, I can use Gram-Schmidt to make these perpendicular. And then I can take my third red vector, I can take the vector projection into that plane and subtract off both of these and get that. So without further ado, let me explain to you how this works. So here is the Gram-Schmidt process. So suppose that I have a basis, some space for it. X1, X2, Xk is a basis. So suppose that I just have some basis for the subspace, and I can do exactly what W is. It's the span of those vectors, plain and simple. Right? I can take this basis and make an orthonormal or orthogonal basis. We take column basis V1 up to Vk. We construct a orthogonal basis as follows. Just take V1 to be the first one, right? Since it's a basis, I know that that's not the zero vector, right? Okay, that was easy enough. Take V2 to be, just take X2 and take its projection on V1. That is to say, X2 V1, V1 dot V1, V1. Notice that this is the projection, orthogonal projection of V1 onto X2, subtract that off for X2. what do I do at the next step? How do I get the third one? This is when I was getting the red vector, the V3. Well, now what I do is I take X3, whatever the third one was in the original basis, and I subtract off what happens when I project it on both vectors. That keep going all the way until I get VK. Well, VK is similar to XK, but again, I subtract how XK projects onto all the others. A dot V1, V1 dot V1, and XK dot V2, V2 dot V2, V2, XK dot VK minus 1, VK minus 1, K minus 1, VK minus 1. By the way, let me give you kind of a little caution here. So what you're doing is you're building up. So first of all, you have V1 is X1. So now I've replaced X1 V1. Now V2 is X2. Notice you should dot this with the new vectors, the new V1, right? V3, X3, X3 dot with new V1, the new V2. Don't dot it with the original thing. You'll make a mess. Let me add some little verbiage to this. Additionally, well, V1, V2 up to VK is an orthogonal basis for W, this will span, and span of V1 up to Vj is equal to the span of X1 up to Xj. So in other words, as you go along the road, the span of X1 and V1 are the same. The span of X1, X2 and V1, V2 are the same. Span of X1, X2, X3 and V1, V2, V3 are the same. And so forth. So you're basically building the same space as you go along. Okay. So let's see this in action. I'm going to do this a couple of ways here. Let's find an orthogonal basis for span of 1, 1, 1, 1, 3, 2, minus 1, 0, and 1, 3, 3. So let's take these four vectors and their span, notice their span is a subspace of R4, right? Gosh, it does say in the Gram-Schmidt process that I need to start with a basis, right? Well, certainly this is a basis for the span of those three, if what?
They're linearly independent.
If they're linearly independent, right? What do you suppose would happen? So I'm just going to trust. I'm a lazy man. I don't want to sit here and figure out if they're linearly independent or not. I'm going to just kind of trust it. What do you suppose would happen if they're linearly dependent?
One of the projections is zero.
That's right, that's right. So one of the, so actually you should get the zero vector out of one of them when you build the Gram-Schmidt process, that's right. Let's see what happens here. So this is playing the role of x1, x2, and x3 in this case. And I'm gonna actually, as we do these computations, which won't be too bad, but believe me, it can get very bad. And I'm gonna show you a couple of tricks of the trade that you might find useful. Okay? Because that's what it told me to do. The other one, or the next one, V1 minus X1 dot V1, V1 dot V1. Oops. This is this should be X2. This should be X2. Okay, let's see what happens. What is X2? It is 3, 2 minus 1, 0. Okay, let's make a fraction here. V1 dot V1. What is V1 dot V1? 1. Are we careful? It's 4. That's right. What is V1 dotted with X2? Well, it's simply just dotting these two, right? Shouldn't it be 4? 3 and 2 minus 1 is 4. I like that, right? And V1 is 1, 1, 1, 1. So this is 3, 2 minus 1, 0 minus 1, 1, 1, 1. So I get 2, 1 minus 2 minus 1. Okay, gut check. Those two orthogonal? They sure are, aren't they? Right? The dot product between these two, 3 minus 3 is 0. Everybody okay with it? Okay. Let's go to the next one. So I'll write this one out explicitly. V3 is X3 minus X3 dot of V1, V1 dot of V1, V1 minus X3 dot of V2, V2 dot of V2, V2. Right? So let's see what shakes out here. X3 is 1, 3, 3, 1 minus, okay, right. V1 dot V1 is 4. I already did that. What is V1 dot X3? It's 8. Look at me and all my integers. I am just living life the right way. Okay. Another fraction. V2 dotted with V2. Not X2, V2. Right? This is what I mean about being careful here. What is V2 dotted with V2? Looks like it's 10s, doesn't it? Do I agree with that? How about what do we got to do here? V2 and X3. So I've got about V2 and this. Tell me what you get. I think that's what I get. Like V2 dotted with, this is the X3 one. It's gonna be 2 and 3 is 5. minus 6 is -1, so it's -2. D2, which is 2, 1, -2, -1. Right? So let me clean this up a little bit. This is 1331 minus 2222. That's going to be plus 2/5. 1/5 minus 2/5 minus 1/5. Everybody okay with that? Let's see what I get here. That's gonna be -1 2/5 and -3/5. That's going to be 3 minus 2 is 1 1/5 is 6/5. That is 1 minus 2/5 is 3/5. And that is -1 -5 6. Not quite as pretty as the other one, is it? But let me do this. -1 2. There we go. Oh my goodness, Quackadol's finally lost his mind. Look at that. Doesn't even have fractions in it. How did I do that? That is correct, right? If I multiply this by 5/3, I get 1. Well, I get -1, 2, 1, -2, right? You can leave the fractions in there, but I'd rather, perform violent acts upon myself, right? Because it's, who wants these fractions in here? Right? What if step 2, I said, what's an orthonormal basis? Much easier to deal with here. Everybody agree with that? So, in fact, let's do that. Uh, 1 1 1 1, because I started with that. 2 1 minus 2 minus 1, right? And -1 2 1 minus 2. By the way, are these orthogonal? Let's see. Well, how about that? These two are orthogonal, so are these. So this is an orthogonal set. Everybody okay? How about orthonormal? Right out by the length, right? And look at me, the length of this is 2, right? Because when I dot it with myself, with itself, I get 4, and the square root of that is 2. So and this one has length radical 10. Those are 2 over radical 10, 1 over radical 10, -2 over radical 10, -1 over radical 10. And this one has the same length, also radical 10. So it's -1 over radical 10, 2 over radical 10, 1 over radical 10, -2 over radical 10. Everybody okay with that? Any questions on that? I'm gonna do this problem again. And all these things. I think that's what my correct numbers there. By the way, what's the difference between this and the last problem? Nothing really, except that I've interchanged X2 and X3. Everybody agree with that? But I want to point out something that's, and of course I could have permuted them even worse, right? I could have put this one in the front, this one in the middle, and that one in the back. But let's just go with this. What happens when I go orthogonal this time? Same starting point, right? So notice that one there. What happens when I do this? This is X2 minus X2 dotted with V1, V1 dotted with V1, V1. We'll see what we get out of this. X2 is 1, 3, 3, 1. This right here, let's check this. V1 dotted with V1 is 4. We've done that till the cows come home. But what's V1 dotted with X2? 8. 8 times V1, which is 1, 3, 3, 1. And so I get X2. Oh, I'm sorry, this should be V1. Out there. So this is 1, 3, 3, 1 minus 2, 2, 2, 2. Right. So I get minus 1, 1, 1 minus 1. So here, as I build these up, we've got check these through orthogonal. I forgot product is in here. Finally, big 3 is X3 minus X3 dot V1, V1 dot V1, V1 minus X3 dot V2, V2 dot V2, V2. So X3 in this case is 3, 2 minus 1, 0 minus V1 dotted V1, once again with 4. X3 dotted with V1 is, what is it? 4. V1, which is 1, 1, 1, 1. Okay, X3 dotted with V2. So what's that? It's like it's -2, right? And V2 dotted with itself, 4. And V2 is minus 1, 1, 1, minus 1. So what I get here is 3, 2 minus 1, 0 minus 1, 1, 1, 1 plus, so that's going to be plus a half, so it's going to be minus a half, a half, a half, minus a half. So I get 3 minus 1 is 2, minus a half is 3 halves. 2 minus 1 is 1 and a half, is 3 halves. Minus 1 is minus 2 and a half, minus 3 halves. And so that's going to be minus 1, minus a half is minus 3 halves. So there's the final one. You see a way I can rescale that to make it easier.
1, 1, -1, negative.
How about that? It's also easier to kind of gut check too, that it's orthogonal, right? We got the dot product, these two are zero, these two are zero, and yes, indeed, these two are. So notice that my orthogonal basis looks strikingly different from the other one. So the moral of the story is, when you do the Gram-Schmidt process, both of these answers are correct. They are both an orthogonal basis for that space, right? But you got a different answer, right? For example, if you look at R2, E1 and E2 is an orthogonal basis. So is the basis 1, 1 and 1, negative 1, right? So orthogonal bases aren't necessarily unique. Okay, any questions on that? Oh, and by the way, here's another orthogonal basis. See if you can come to this one. 1, 0, minus 1, 0, 0, 1, 0, 1, 1, 1, 1. We didn't do any Gram-Schmidt on that one. Where did that come from? By the way, would you agree that this is orthogonal? What's not clear is its basis for these, because it's not even clear it's the same subspace, right? However, it is. By the way, would you agree that that's the easiest orthogonal basis of all the ones I have listed? Because it's one's got the most zeros, right? Where did this come from? This came from me making up a problem. I'll make up all my examples kind of by scratch. So I started with this orthogonal basis and I added it together in various ways to come up with this. And then I started with this seed and it gave me actually a different orthogonal basis when I started. Right. So if you're clever enough, you might be able to Gram-Schmidt this basis out of it, but you obviously can't start where we did before. Okay, but all these answers are good. Okay, any questions so far? There, moment. Okay, so here's my promise application. So I want us to explore how to do a QR factorization. So this is kind of a neat way. So if I walk up to you on the street and I give you a matrix under a certain condition, you should be able to factor it into a QR factorization. Why do you care about doing this? Well, for square matrices, it's useful to find eigenvalues. It's good for computational effectiveness. And you will see that the way that I factor this actually does have some computational advantages to it. There's one condition you need. QR factorization of a matrix. What you need is with linearly independent columns. If you start with a matrix that does not have linearly independent columns, then you'll run into a problem, because what you'll do is when you Gram-Schmidt, this is actually an application of Gram-Schmidt, and I'll tell you how that works. You'll get a column of zeros. So this means that for linearly independent columns, what can you say about the relationship between the number of rows and the number of columns in this matrix? That's a possibility, but more generally,
there are more rows, columns.
right? There's at least as many rows as columns, right? So let me just go ahead and spit this out, and then I'm just gonna. There's a proof in your book. It's not super enlightening because actually, through my example, I think you're gonna see why this works. Let me give you kind of a theorem here that governs this. So, theorem. Yeah, A is in R, M by M. and has linearly independent columns. And by the way, even if you forget this little fact, it's probably going to become obvious that you need this later in the statement of the theorem. So if you have a matrix that has linearly independent columns, then A can be factored as A is QR. And let me tell you what these animals are. With so Q is the same size matrix as your original matrix. As your original matrix A. Can somebody tell me what size then that forces R to be? It has to be n by n. So R is going to be a square matrix. But Q is the same size of this. Is a matrix with columns forming and orthonormal. And I do mean normal here. It has to be orthonormal basis for the column space A. This is the phrase that could catch you, right? Because if A doesn't have linearly independent columns, then the columns of the same size matrix can't form an orthonormal basis for it, right? And R is matrix n by n, has to be that to fit the size of A and be able to multiply by Q. Is upper triangular with positive inference on diagonal. Okay. So if you have any let me make it more. So it must be true in this matrix, the number of rows is at least as big as the number of columns. But this condition alone does not mean that the columns are linearly independent. For example, you could have a matrix that is a single column of zeros, right? And there's your bad example there. Now, I'm going to show you. So here's how you do it. So here's Jim's practical corner. One. Because in the theorem, it describes for you exactly what Q has to look like. It's just filled up with the orthonormal basis for the column space of A. So just take the columns of A and turn it via the Gram-Schmidt process into an orthonormal basis. Yes.
Would you need to find the column space of A first, or can you just assume that all the column, like, if you can just check if all the columns?
That's why we said the concept of linearly independent. So, yeah, so the column space is generated by the columns, right? It's just all the columns. There could be a zillion columns, right? That generates the column space, spans it. But when I also said I demanded the theorem to be linearly independent, that means exactly, because what's going to happen is if they're not linearly independent, one of the columns is going to be a linear combination of the other, and the Gram-Schmidt process is eventually going to give you a zero vector. So that's a good question though. So we build Q via the Gram-Schmidt process, assuming that they're linearly independent. Now, how do we find this one, right? This looks like a pain in the butt, but it's actually quite easy. And here's why. Let me read this. R is just Q transpose A. If I explain why that's true.
It's the equivalency over there.
Well,
You want to solve,
this is what you want R to be. Just take R and multiply Q transpose times whatever A was. That gives you the R. Why does this work? Well, the reason this works, and this is kind of the big thing, multiply both sides on the whatever side this is, the left by Q. Right? And so what does that mean? What is what is Q transpose and why?
Identity matrix,
It's the identity. How come?
because Q transpose is Q inverse.
Oh, well, yeah, that's so, because the reason is because M is greater than or equal to N and Q has orthonormal columns, right? So this turns out to be, let's see, this transpose, it should be IM, I guess. Yeah. And so there's your factorization. So you can you build Q by using the Gram-Schmidt process and say, oh, there's my Q. Then take the transpose of it and multiply it by your original matrix, bang, there's your R, and that's your QR factorization. Right. So let's actually see this work. And I'm gonna piggyback off of this example we had earlier. Let's let A one 3 2 minus 1 0 and 1 3 3 1. Somebody tell me how I know that this has linearly independent columns. Because I've already turned this into a basis using Gram-Schmidt, so I know that this has to feel linearly independent set, right? So how do we build Q? Well, we've already done this, right? We got what did we get? Oh, and I do want it to be orthonormal because that QT being the identity, you need orthonormal. Orthogonal is not going to cut it for you. Orthogonal will mess it up by, it'll scale it all wrong in the different coordinates. So let's see what we get. 1/2, 1/2, 1/2, 1/2. And the next one we got was 2 over radical 10. 1 over radical 10. Minus 2 over radical 10. Minus 1 over radical 10. And finally, I got minus 1 over radical 10. 2 over radical 10. 1 over radical 10. Minus 2 over radical 10. Right. This is what we got. Right. Yes,
So does it matter, like you said, that you could find an orthonormal basis by like two different ones or orthogonal, if you switched B2 and B3? Or I'm sorry, yeah, B2 and B3.
yeah, but keep it in the same order. Yeah, I think am I anticipating your
Yeah,
question correct? Yeah, that's right. I put them in there in the same order. Okay, so now we have Q. And I don't think it needs you anymore. Let's see what Q is. It's just this thing. 2 10. 1 over radical 10 minus 2 over radical 10. 1 over radical 10. And finally, minus 1 over radical 10. 2 over radical 10. 1 over radical 10. Minus 2 over radical 10. That's your Q. And R should just be Q transpose A. Let's write this out. Q transpose. Now let's multiply it by A, which was 1, 1, 1, 1. 3, 2, minus 1, 0, 1, 3, 3, 1. And we could get a 3 by 3 matrix here. This should be our R. Let's see what we get. 1/2 times this, that comes to 2, doesn't it? This row comes this column. Here we get 3 halves and 1 minus a half. So that's going to be 2, another 2. Here I get a half and 3 halves is 2, and there's another 2. That's 4. 3. Yes.
Didn't it say in the theorem that R was supposed to be upper triangle? Or no, never mind, I'm stupid.
It will, actually, I'm glad you said that because it better be.
Right.
And it should have positive values on the diagonal,
I
right?
flipped up, I messed up upper and lower triangular, so no problem.
So here we go. This row, we'll see everything's going to have a denominator of radical 10. So I'm going to have a 2, 3, minus 2, minus 1. See, there's your orthogonality kicking in, right? Because this times this, it should be orthogonal. Bang. And that's why I get the 0 there. Right? This row times this column, which is where it came from. Again, over radical 10, I'm going to get 6 and 2 is 8. And 2 is 10. So I get 10 over radical 10, which is radical 10. In that positive entry here. And finally, this row times this column should be, that's going to be 2 and 3 is 5. Minus 6 is -1, negative another 1, minus 2 over radical 10. Finally, the first 2 should be 0 this time. This times this, again, orthogonal, and you can actually multiply it out and see. This times this, orthogonal it should be, but let's see, -3 plus 4 over radical 10, -1, back to 0. And finally, this times this, I'm gonna get over radical 10, -1 and 6 is 5, and 3 is 8, -2 is 6 over radical 10. And there you have it, over triangular, positive interest on diagonal. Any questions on it? Okay, practice the Gram-Schmidt. I pretty much guarantee you're gonna have to do at least something on that on the final. It's not a hard process, but it takes more getting used to, so run that by yourself a couple times. Have a good one, we'll see you on Wednesday.